My name is Alex, and I'm like in love with LLVM for many years, and I like it because I can work on some like super fun side projects. And kind of as a disclaimer goes, these side projects are not related to my general full-time employment. So today I want to talk a little bit about the project that is called Dragon Ruby. It's a small mostly like 2D-oriented game engine that I'm building with some friends. And it kind of looks like this from the like high-level overview. So on the left, you see the game engine itself. It's built in C and Ruby. So the APIs and some runtime part is written in Ruby itself. So the game engine, this is what we are like shipping to our users, to kind of our customers. They then can write their games in Ruby itself. Specifically, my part of this project was to implement the C extensions. And one of the reasons that some people complain that Ruby is slow, and we just gave them this hedge that, okay, if you like truly care about performance, you can go and do some C extensions for your game. So yeah, those end users, they then can bundle this all together, like we also provide some tooling and ship this game to their users in the end. When I was working on this C extension stuff, I started thinking like, okay, if we're talking about optimizations, then I would actually like to optimize this code somehow. And while the runtime, we can optimize it all together with like link time optimization and all those fancy stuff. The extensions themselves, they are like separate from the engine, right? So to solve this problem, we would have to ship the runtime in some other common form like LLVM Bytecode, for example. But what actually struck me here when I was thinking about this problem, what about all this Ruby code? It's like not optimized at all because we are using interpreter, and most of the Ruby implementations are about interpreters. So yeah, I asked myself, how can I solve this problem? And the solution is obvious, you just build a compiler, right? So as a real engineer, I nerd-sniped myself into solving a problem that no one ever has asked me to solve. So the first question that I had, okay, like now I want to build a compiler, and how do I do that? And while my talk is titled Ruby, on this slide I'm talking about a dynamic language, because I believe the same approach is applicable for other languages as well. In fact, I thought that when I would be done with this project, I can go and build a compiler for Python, because Python deserves that. Turned out I'm late to the party. There is some group of smart people doing that already. So getting back to the compiler, I started like kind of backwards, like what do I want to have? And the good example, like Clang, for example. So you take C code, you feed it to Clang, you get the executable as an output. But if we zoom in a little bit, then it has like the following structure, right? So the source code needs to be parsed, transformed into some AST form. Then optionally, there might be some intermediate representation. This intermediate representation then converted to the machine code. The machine code linked together, and it's also linked with the language runtime, right? Then you get the executable. So to build a compiler, I would have to fill in all these gaps and to implement all of it. But there are like two problems. I'm not very smart, and I'm very lazy. I don't want to implement all of this from scratch, right? So, for example, for the AST and parsing, Ruby is known for having like pretty crazy grammar, and it's like super hard to write proper parser that is production ready. So instead, I should probably be just using some existing thing. The same goes for like machine code generation, right? This is kind of solved problem these days. We have like lots of compilers, we have LLVM. So this is also, I think, I can reuse. The next thing is the language runtime. It's certainly an interesting problem to solve, like to build a full language runtime. But if I build my own, then it will probably be incompatible in ways with some other Ruby implementations. I don't want that. I want to be part of the existing ecosystem. So again, as with like the parsing, I decided to use the existing language runtime. And it's kind of yellowish on this picture because I think I would have to extend it and modify it to fit in my needs. Okay, so the last part is this IR, like intermediate representation, right? And at this point, it's more like abstract form. It's not like nothing specific. And this is what I actually have to implement because there is nothing like that, right? Otherwise, there would be existing compiler for Ruby already. So with this in mind, I took a look at the language runtime, like Ruby implementation that we are using for that game engine. And in this case, actually, like most of the Ruby interpreters, they work like this. There is the AST code that is being parsed, then it's converted into the bytecode, and this bytecode is then being fed to virtual machine. This virtual machine does the execution, and you get side effects as an output. So what is the bytecode, right? Again, there are several implementations, and if you ever run some Ruby scripts on your machine, like Linux, macOS, whatever, that was probably MLIR Ruby, which is kind of the Ruby implementation, and it uses stack-based bytecode, and in our case, it's mRuby, which is like so-called embedded Ruby, where you can take this Ruby runtime and embed into your application. And the difference is that mRuby uses register-based VM, where you can see the just example bytecode here, that all the registers are marked explicitly like R1, R2, and so on. So what does VM do in this case, and how it's implemented under the hood? It's usually just like very, very huge switch statement that has lots of cases, like one case for each opcode. So if I want to compile these 4 bytecode instructions into some machine code and produce some single executable, what I can do actually is to just emit some C code. It would look like something like this, right? And in fact, this is how I started doing this, and it works pretty well for some basic stuff. Yeah, so let me just show you one example of this. Yeah, I think that was like the very first code, like piece of code that I wrote, and I compiled it down to C. It looked like this. Right, I mean, I don't expect you to like read or understand what's going on there, but this is the idea, right? So you could use C as an intermediate representation. So, and coming back to this picture, I can use bytecode as my like sort of AST thing. Then I generate C code, feed it to Clang. As a linker, I also use Clang. Again, it works pretty well for some basic stuff, but then I just found myself implementing some arrays of maps of arrays to track some data. So effectively, I was reinventing some other high-level intermediate representation in memory one so that I can do some analysis. So this actually like didn't work well in the end because I also want to do some analysis on the bytecode level, and C doesn't really allow me to do so. But yeah, there are lots of benefits, right? Like debuggability and so on and so on. So what I did next is realize that, okay, there is this thing, MLIR, like everyone is talking about it. And I thought, okay, maybe I can apply this in this case. And it turned out that I kind of can do it, but there are some like the differences, right? This is the original C code, or rather example. And if I want to convert it to MLIR, then I cannot do this way anymore because MLIR is an SSA form, right? So I cannot just like override this R2 register variable like this. So typical solution for this thing is to use some sort of like load store combination where whenever you need to read something from register, you load from it. Whenever you need to write something to register, you like use store, right? So this would work, but it kind of defeats the purpose because I want to, again, I want to run some analysis and I don't want to overcomplicate things in this regard. It turned out that this is kind of like trivial data flow problem, because at every point in time in the program, I know that which instruction uses which register and which instruction defines which register. Yeah, kind of as important side note, this is the case with mruby bytecode, because I know at compile time exactly what is being written, what is being read. If there would be some indirect addressing mode, then this would not going to work. I would have to use some different combination of things. Anyway, so what I've done is I just extended those MLIR operations, basically, yeah, with some attributes like defines uses, and then by default, everyone uses some like dummy instruction. Then I run this data flow analysis, and I know exactly which value should be used in which case. And yeah, that works like this. Again, this approach, like if I just applied blindly like this, it breaks terribly if we have some branching. And with branching, like with MLIR, there are like block arguments. These are not like, there are no phi instructions and so on. But again, in this case, the problem turned out to be trivial. Like if something is used but not defined in this basic block, then I just say, okay, it must be coming from the predecessor. And then all the jumps from the predecessors, they kind of use what is being required, right? Yeah, I'm going to share a link in the end with some more details, because I think, yeah, there is a better explanation on the website. Anyways, so again, I do run this data flow analysis, and obviously when there are loops, you run it until fixed point and so on. But at this point, we can just assume that I've got like exact SSA form MLIR representation of this bytecode. So in the end, yeah, these instructions, I think like pretty much every instruction in this dialect, they have either defines and uses or both. Yeah, there is also address, which I need to reconstruct the control flow graph because of like jumps and so on. And so far, this dialect resembles, like it's very close to the actual bytecode, but it's pretty far in some cases from what the language runtime provides and all the APIs. So in the end, I had to create another dialect, which is kind of lifting this bytecode to a more high-level thing, and also mixing it all together with some existing dialects like control flow and arithmetics from MLIR, like out of the box. Then in the end, all this stuff is getting lowered to LLVM dialect from MLIR. And that MLIR, that LLVM dialect then is translated to LLVM Bytecode. Wow, confused myself. So again, this picture now looks like this. The Firestorm is like working name of this Ruby compiler. But again, I'm using my compiler to produce MLIR, then I lift it or lower it to LLVM, and then I use Clang to compile it all together or link it into a single executable. So if we, again, zoom out a little bit, then this kind of design has a nice feature, because in the end, right before going into the executable, I have LLVM for both sides. Right, the C code here is the language runtime, and this Ruby and MLIR code is the actual like Ruby code. Then I can link this together and do cross-language optimization on LLVM level, which is kind of like blink time optimization in this case. And yeah, speaking of optimizations, this is a huge to-do on my list, and I started with optimizations, like that was like one of the goals of the project, to get something fast. But right now, I'm targeting to get to the baseline so that everything works, right? Because right now, I can do some optimizations, but if I don't have full compiler implemented, it just doesn't make sense, because implementing some other feature may break those optimizations. But just to give an example, like besides things that I can get kind of out of the box, like default compiler-based optimizations, There are some opportunities to optimize the bytecode itself. For instance, yeah, there are like 2 examples where like 5 instructions, 5 bytecode instructions generated, and they can just be all combined together into one constant thing. Yeah, and this is, I'm going to show a quick demo real quick. Speaking of performance, yeah, I think it's here. So again, this is like micro benchmark, right? It doesn't make any sense. It just, I could not resist from doing that. And the point here that I can compile this code differently because I produce the language runtime can be compiled into the machine code right away, or it can be compiled to LLVM bitcode. And then if I do this LTO thing, then I get a pretty nice speed up. If I don't do this LTO stuff, then things are a bit slow. So yeah, this is just like run from several programs. So the last 2 ones are this micro benchmark with LTO and without LTO. This one, the first one is like 30 milliseconds without LTO, but with LTO it's like 16 milliseconds, which is on par with what actually mRuby interpreter does. So at this point, I think performance is kind of terrible, but we are on par with the interpreter, so it means that everything, any other improvements that we add on top, that they should speed things up. Okay, so where we are and yeah, the next steps. Right now, I've got almost all the opcodes implemented, and there are like only 3 left. And these are the most annoying ones because on the left you have code in C++, there is some lambda call, and if you return from lambda, then it just returns from lambda, right? But in Ruby, you can actually, there is special bytecode instruction return from block, which would just return not from lambda, but from like outer function. So these 2, like C++ version will print function will return 0, and the Ruby function will return 42. I implemented exception support because in mRuby, they use set jump, long jump. There are no finalizers. I don't need to unwind anything. And I thought that's great because it like simplifies things a lot. But in this specific case, like return 42, like on the right, this lambda call and the outer function call, they are on different stack frames. And if there is some stack frame somewhere in between with like try, catch, finally equivalent of Ruby, then I have to run those finalizers. So now I actually have to unwind this stack, and this is, yeah, makes me procrastinating a little bit. So these 3 instructions, they actually use quite often in the code base. So this is this mRuby implementation. I can successfully compile like 150 files out of like 180, and like, yeah, 15K out of 20K lines of code. So, but my actual goal like is to make all these standards tests pass, because once I do that, then I can say that my implementation is complete, and I can run some real benchmarks, and I can work on optimizations, and actually then conclude like with yeah, improve some UX. Because in this case, if I want the users to be able to do this LTO stuff, then I should ship language runtime in the form of LLVM bitcode. And I also want to do like some cross-module optimizations and the MLIR level. So I need to ship this somehow in a nice way and do the linking and so on, so on. This is probably not like hard problem, but just annoying one. Yeah, we're running out of time, so just gonna quickly go through pros and cons of MLIR. In my opinion, cool thing is dialects. You can design something like nice IR for your specific domain, which is cool. Debug information, yeah, I didn't need to do any like to deal with the debug information generation for the executable, but I just got it out of the box from MLIR because I provided those locations for operations. Some APIs on LLVM are simpler. with the LLVM dialect, and it's much more pleasant to work with than with the LLVM IR APIs directly. And it has like fantastic community. Like whenever I have some question, I just ask it on Discord. There is like almost always an immediate answer from someone. There are some cons, yes, again, the dialects, because there is so much space and I can do like whatever I want, and I don't know if I do the right thing, right? So I designed these two dialects. Now I think that, yeah, they're like probably not good, so I should redesign them. But for those watching here live, the next session in this room will be from Jeff about exactly designing dialects for front-end compilers. Yeah, the project is relatively young, so you have to understand that some things are not implemented, there are some rough edges, and so on and so on. As a consequence, documentation is lacking, and it somehow feels that it's like ML-oriented, because everyone is talking about machine learning, accelerators, dark silicon, and stuff, but it's actually a great fit for like traditional compilers. So I would, yeah, I think this is kind of missed marketing opportunity, right, to advertise MLIR for traditional compilers. I know Flang compiler uses it, but I think like more projects would benefit from that. Okay, that's it. If you have any opinions, like how would you solve this problem of compiling the dynamic language, please send those opinions my way. That would be appreciated. Thank you.
So, any questions for Alex?
Hello, fantastic talk. This is really fun to learn about. I was kind of curious as to how things like memory management is done. Is it that the runtime has a GC and so you don't need to worry about it at the MLIR level?
Yeah, in this case, runtime has GC, and it's tree-color incremental garbage collection. And what I need to do is to just emit the right calls to this GC API from the language runtime.
Okay, cool, nice.
Yeah.
Anyone else?
Yeah, thank you for the talk. It was really interesting. I was interested actually how you solved several of the problems that you have when you generally implement a dynamically typed language. But you might have gotten away with just using the bytecode. Like, for example, do you have any issues with big nums, or I don't know if I don't know much about Ruby, but if Ruby has continuations or something like that, how you implement those, or what were the features that are part generally of a high-level dynamically typed language that were more challenging to implement?
Yeah, I think it's again mostly like part of the runtime, right? So for continuations, Ruby has fibers, and they're not supported yet, right? When I generate code that kind of calls the fiber APIs from the kind of C side, then it fails terribly because it was not designed to work this way, right? So I would have to adjust the runtime for that. And yeah, I think the same goes for pretty much any other feature.
Okay, yeah, thank you very much.
Yeah, a very interesting discussion. I'm curious whether you've explored in the direction of how Java virtual machines work. Specifically are you familiar with the EuroLLVM project?
Yeah. I know EuroLLVM, I know Truffle.
Yes.
There is also RubyMotion. I mean, I did explore some options, yes. But for this specific case, I just decided to kind of start from scratch, so that to get some like as an exercise for myself, right?
Yeah. Okay. Thank you.
Yeah. Thank you for the question.
Probably time for one more question, if anyone has one. Okay, great. So let's thank Alex one more time.
Thank you so much.